Today, we're not just touring ductwork. We are going to prove, with math, whether a local exhaust ventilation system, or LEV, is actually protecting workers. You know, this isn't just about checking a box for compliance. This is about real competence. And if you're designing a system, or maybe you're studying for the CIH or CSP exam, this is exactly what you need to know.
This quote right here, it just perfectly sets the stakes. I mean, guessing is not a strategy when someone's health is on the line, right? The calculations we're about to walk through are the absolute bedrock, the fundamental proof of protection. It doesn't matter if you're designing a new system, checking an old one, or prepping for that big exam.
So we've got a really clear roadmap for this. First, we'll talk about the mission. Then we'll get into the fundamental physics of airflow. After that, we'll tackle the real-world complications, things like distance and hood design that can trip you up. Then we'll run through some actual practice calculations. And finally, we'll tie it all back to why this is so critical for your career.
Okay, so what is our mission today? It's to give you the tools to prove, with hard numbers, that an engineering control is actually doing its job. This is how you verify for sure that the system is pulling harmful stuff away from workers, and not just, moving air around the room.
And we're not just pulling this out of thin air. Our whole approach is anchored in the industry's most authoritative sources. We're talking the ACGIH Industrial Ventilation Manual and the ANSI/ASSP Z9.2 standard. These are the gold standards, and hey, not so coincidentally, they're also the basis for a ton of certification exam questions.
All right, let's get into the fundamentals. Every single effective LEV system is built on two main principles: capture velocity and airflow. Really, it all comes down to two simple questions: how fast is the air moving, and how much air is moving?
First things first, let's clearly define the star of the show, capture velocity. I want you to think of it like the minimum speed you need to win a tug of war. On one side, you have the LEV system pulling the contaminant into the hood. But on the other side, you've got all these random room air currents trying to pull it right into a worker's breathing zone. Capture velocity is the speed needed to make sure the LEV system wins that battle every single time.
Now, what's really fascinating here is how dramatically that required speed can change. This table, which is based on ACGIH guidance, shows that for something gentle, like evaporation from a tank, you need a pretty low capture velocity. But look at something like grinding, where particles are literally being thrown off at high speed. You need a much, much higher velocity. We're talking up to 2,000 feet per minute just to grab those particles and pull them into the hood. The energy of the source totally dictates your design.
And all of this, believe it or not, is governed by one simple but incredibly powerful formula: Q equals V times A. So Q is your total airflow volume in cubic feet per minute. V is the air's velocity, and A is the area of the hood opening. Seriously, understanding the relationship between these three is the key to everything else we're going to talk about.
And this right here perfectly illustrates a super common and, frankly, dangerous mistake. People often assume that a bigger hood automatically means better capture. But look at the physics. If you increase the hood's area, that's A, without upgrading the fan to increase the total airflow, Q, then basic math tells you your velocity, V, has to drop. You've just made the system less effective, maybe even completely useless.
But Q equals V times A, that's just the starting line. In the real world, a system that looks perfect on paper can fail miserably. So let's look at the two biggest culprits: distance from the source and the actual design of the hood itself.
Just look at this diagram for a second. It shows that air velocity doesn't just decrease as you move away from the hood, it absolutely plummets. I mean, at a distance of just 1 duct diameter away, the velocity can be as low as 10% of what it is right at the hood face. Think about that. A worker standing just a few inches too far away might as well have no ventilation at all. Now, a flange helps, you can see that on the right, but that decay is still incredibly fast.
Okay, the next complication is something called hood entry loss. See, as air gets pulled into the duct, it creates all this turbulence right at the entry point. That turbulence is just wasted energy. It's work the fan has to do that isn't actually helping to capture contaminants. And the shape of the hood is what determines just how much energy gets lost.
And here's a great side-by-side comparison. A simple, plain duct opening, it's a terrible hood design. You get tons of turbulence and energy loss. But in contrast, just adding a simple flange, or even better, a smooth bell mouth shape, lets the air flow in smoothly. This minimizes that energy loss, which means you can get the same capture velocity with a smaller, cheaper fan. Design really matters.
All right, for all of you studying for the CIH or CSP exams, this formula right here is your new best friend.
It relates the hood entry coefficient, which we call CE, that's a measure of efficiency, to the hood entry loss factor, F. A perfect loss-free hood would have a CE of 1. A really terrible hood has a much lower number. Exam questions love to hide velocity loss in the hood's design.
Okay, enough with the theory. Let's shift gears and actually apply this math to a couple of practical exam-style examples.
So let's start with a pretty simple example. We've got a solvent station with a 2-square-foot hood. We look at our ACGIH tables, and they tell us we need to capture velocity of about 100 feet per minute for this process. We just plug those numbers into our formula, Q equals V times A. So that's Q equals 100 times 2, which gives us a required airflow of 200 CFM. Simple, right?
But, and this is the huge takeaway, that 200 CFM is the ideal airflow you need right at the hood's face. It doesn't account for any of the real-world problems we just talked about, like that hood entry loss or any friction in the ductwork.
Now here's a typical exam problem. Using a more complex formula that factors in airflow and area, you're asked to solve for X, the maximum effective capture distance. This is where you have to work backwards from the fan's total airflow to find that real-world point where the velocity is still high enough to work. So go ahead and pause here for a second and think about how you'd set this problem up.
Okay, let's try a tougher one, a grinding operation. The required velocity is way higher, let's say 300 FPM. And we have a 1.5 square foot hood. Our theoretical airflow, Q equals V times A, would be 450 CFM. But once you factor in all those real-world inefficiencies, the hood entry loss, the friction in the ducts, the actual fan you need might have to be rated for 600 or even 700 CFM just to get that useful 450 CFM of work done at the hood. This is exactly why you can't just guess.
So, why do we go through all this trouble? Let's talk about the payoff, because this directly impacts your professional life, from exams all the way to your potential liability.
So why does this math matter so much? Well, first, it's on your certification exams. Second, it's the kind of proof that regulators and employers expect to see. Third, it's how you validate your air sampling data. I mean, think about it. If your samples show overexposure, but you claim the ventilation works, you need these calculations to defend your position. And finally, if you can't provide that proof, you open yourself up to some serious professional liability.
And remember where LEV fits into the big picture. It's a powerful engineering control, ranked way above things like administrative changes or just handing out PPE, but it only earns that high rank if it's properly designed, installed, and, most importantly, verified through calculation and measurement.
And that really brings us to this critical takeaway. An unproven system, it's not really a control at all. It's a box-ticking exercise that provides a dangerous illusion of safety, all while potentially letting workers get overexposed day in and day out.
So I'm going to leave you with this question to take back to your own workplace. When you look at your ventilation systems, can you say with certainty that they are providing proven calculated protection? Or are they just moving air? As we've seen, the difference is everything.